All right, good morning, everyone. I'm very happy to introduce today's seminar speaker as part of our MSc seminar series and the joint materials seminar series of the U of A. So welcome to everyone online as well. So I'm very happy to introduce today's speaker, Dr. Katie Harrison, who is a principal member of the technical staff at Sandia National Labs in Albuquerque, New Mexico. She is one of the battery experts at Sandia. So she did her undergrad at UCSD in mechanical engineering, and then her PhD at the University of Texas at Austin. She was working in the battery lab there, and her focus area was material science. So since she's been at Sandia, she's worked on many different battery chemistries, including lithium ion, sodium ion, silicon anodes, lithium metal anodes, lithium air batteries, and conversion cathodes. So really a lot of different materials. And so her talk today will be focused on lithium anodes, and we really look forward to seeing all the exciting research. Thanks.
Thank you. Thank you so much for inviting me. It's really fun to come and visit you, and I've had a lot of fun talking to professors and students so far. So today I'm going to talk about my research on the effects of pressure on lithium anode performance. So first, I'm going to give you a little bit of background about Sandia National Labs and national labs in general. When I was a student, I was always interested to hear how people got to where they are in their career. And hopefully that'll give you some information about working at a national lab and how you can make that a career path. And then I'll get into some of my research. So this is a schematic of the Department of Energy National Lab System. There's a lot of national labs in the country. Sandia is one of the biggest, and that's the one that I happen to work at. You can see that the National Lab System has work that spans in their mission space from science all the way to more advanced technology. And where each national lab sits on that spectrum sort of varies with their particular mission. Every national lab has a little bit different of a mission and what they're sort of responsible for, but they're all federally funded research and development centers, which means there's a long-term strategic partnership between the government and the national lab system, in which the government sort of picks and chooses what they think is really important to keep as core competencies to support national problems in America. And you can see that the specific part that Sandia works on is it's a multi-purpose security lab. Our business is really all about national security, and we work on a lot of problems that impact that area. So I also want to talk about where national labs fit in sort of the broad spectrum of what we do in the R&D community. You can see that there's universities, there's industry, there's national labs. We all do research and development, and they span from discovery science to all the way to commercialization. And industry is really the best at commercialization. They're good at taking these scientific ideas that people come up with and advancing them into actual implemented technology. Universities tend to be the best at doing the fundamental science, and national labs sort of fit somewhere in the middle. We work a lot with universities, we work a lot with industry, and we often sort of fill a gap between those areas while sort of working across the spectrum. At Sandia National Labs, we specifically have facilities across the nation. We're one of the biggest national labs. Our main site is in Albuquerque, New Mexico. There's a picture of the main site shown there. We're located on Kirtland Air Force Base. And we also have a large site in Livermore, California, very close to Lawrence Livermore National Lab. We have a bunch of other sites throughout the nation. We have one in Hawaii where we do a lot of rocket launches. So that's a kind of fun thing to get to go and see. And then we have other sites that do various other parts of Sandia's mission. Sandia's history is really traced back to the Manhattan Project. A lot of the national labs trace back to the Manhattan Project. So this is the project that was used to develop nuclear weapons during World War II. And a lot of this work was done at Los Alamos, but there were many other national labs or what have become national labs involved in that process. Sandia didn't exist when the first nuclear weapons were being developed. But in 1945, Los Alamos created what's called the Z Division. And the point of the Z Division was to make all the non-nuclear components that go into a weapon system. So a nuclear weapon, of course, has a physics package that includes all of the nuclear reaction, the nuclear fission material, but there's a lot of other engineering that has to go into a weapon system to actually make the nuclear weapon work only when you want it to and not when you don't want it to. And so the Z division was sort of responsible for all of those ancillary components that make the weapon work and get everything to work the way that it's supposed to. In 1949, Z division sort of turned into Sandia National Laboratories. And that's when we were really born and started being called Sandia. Now, national labs are all government owned, but they're contractor operated. So we always have a company or a university that operates the national lab system, provides upper management, vision, training, all that sorts of stuff. But the government owns the buildings and a lot of the information and technology that comes out of it. So from 1949 to 1993, we were operated by AT&T, then Martin Marietta, Lockheed Martin, and now we're operated by Honeywell. So we were born to work on national nuclear security problems and specifically the non-nuclear components of nuclear weapons. But we've expanded our business quite a bit throughout the several decades since then. So in the 1950s, the goal of Sandia and sort of our mission was really responding to the threat of the arms race that was going on during that time. So there was a lot of nuclear weapon development, engineering, testing to develop other kinds of nuclear weapons and more different varieties. Then in the 1960s, we had the Cuban Missile Crisis and the Vietnam War. And so every time there's something going on with national security in the world, the national labs sort of come to address that, and the government tells us, okay, we want you to expand your mission into new areas. So that happens a lot with Sandia. In that time period, we were working on developing the nuclear weapons stockpile, diversifying the type of weapons, and building up the number of weapons to respond to these crises that were happening in the world. In the 1970s, there was the energy crisis where there wasn't enough petroleum, people couldn't drive their cars, and it became clear that sustainable energy was going to be an important part of our future if we wanted our country to be able to run the way that it normally did. And so Sandia got involved in understanding how to do energy research and wanting to address the sustainable energy technologies that could solve some of the nation's problems in those areas. So that's how we got started there. And then in the 1980s, that brought about the end of the Cold War. And so we weren't quite as dependent on nuclear weapons. So we started doing a lot of other things for national security and defense. We worked a lot with the Department of Defense and did things like missile defense, for example. In the 1990s, we grew that business. There was a lot of stockpile stewardship. So there's still nuclear weapons, but we're just sort of keeping them up and running and making sure that they still work and are being safely stored. And then in the 2000s, with 9/11 happening, there were a lot of anthrax threats and things like that. We started getting into broader national security work to address a lot of different types of problems, including things like terrorism. Then today, we really consider ourselves a multi-mission lab where we do a lot of things. So we do life extension programs or LEPs on nuclear weapons to make sure that they could still be used if they ever need to be. And we work a lot in cybersecurity with the growth of computing and the internet and all of the threats that come with that. There's a lot of need for cybersecurity to protect our national interests. We do a lot of bio work for things like bioterrorism. We do a lot of satellite work. There's a lot of things you can learn from having satellites and working in the space industry. It's very important for our national security. And then we work in anti-terrorism type of. So to kind of give you a breakdown of the official programs and portfolios we have at Sandia, we still have our nuclear deterrence mission. That's always been the core of our business. But we also work in global security. We work on a lot of DoD type of national security programs. We work in energy and homeland security. That includes things like grid energy backup and things like that. And then we have an advanced science and technology division, and that's where a lot of my type of work lies, where I do a lot of fundamental research and don't work in one of the mission areas, But they like to have scientists that are working in all of these areas. So we keep up to date on what's going on in the research community, what new technologies are coming out, and make sure that we're at the forefront to come and help solve problems when our mission areas do have those problems. So in terms of a budget breakdown, Sandia has about a $4.5 billion budget in FY21. Like I said, this is one of the largest national labs. We have 14 or 15,000 people. And we work on a lot of different stuff. Our core business is the National Nuclear Security Administration weapons work, like I mentioned before. But we do a lot of stuff with the Department of Defense, the Department of Energy. We work in non-proliferation. Some of my work sort of falls into this other DOE in either the science or the energy efficiency and renewable energy area. So there's a lot of stuff that we do, and we're a very diverse multi-mission lab. You might wonder how we get funded to do research at Sandia. A lot of those categories that I just showed you, and a large part of our budget is doing mission-related work for the government in our national security missions. But we also have people like me that do a lot of fundamental research. And so there's a couple ways that we're funded. Internally, we have funding mechanisms, and externally. Our main internal funding mechanism for research and development work is called LDRD program, which stands for Laboratory Directed Research and Development. And this program is really designed to enhance the lab's capabilities to address future R&D needs by funding high-risk concepts that could be game changers in some of the technology areas that we care about for national security. We have a number of research foundations: bioscience, computer and information sciences, earth science, engineering science, materials science, nanomicro, and then this radiation electrical and high energy science. And those are all areas that Sandia sees as a priority. I work a lot in the materials science area, and I'm in the materials science center. So that's sort of the one that I work in the most. And then we also have mission foundations where we have specific problems that we're trying to solve in each of these mission areas that we care about. And there will be calls for proposals every year in this LDRD program. And we do interface with universities a lot in this program. We have Arizona State as one of our university partnership target schools. So this is an opportunity for people at ASU to get involved and work with Sandia. And a lot of our university partnerships come out of this LDRD program. Candace works on one of them with us right now. So this is a real possibility for collaboration that we really like to get universities involved in. External funding is also a possibility. We don't always have the same things that we can apply to as you're used to in universities. For example, we don't apply for NSF funding, and you guys do. But a lot of the other stuff, there will be calls that are sometimes open to everybody, sometimes are targeted towards national labs, sometimes are targeted towards universities. Some examples in my field in particular in energy storage are the DOE Vehicle Technologies Office. I've worked a lot with them. ARPA-E is another one. A lot of people work with Office of Electricity, and then the Office of Science. And two examples that I've particularly worked on with the Office of Science are the Joint Center for Energy Storage Research, which is an energy innovation hub led out of Argonne, but that Sandia also played a role in. And this was a very large project across the nation with lots of universities and national labs. And then there's a lot of energy research or energy frontier research centers that Sandia has been involved in, and I'm sure ASU as well. So those were some of the ways that you can work with Sandia. And I wanted to specifically talk about ways that faculty and students can work with us. So as a faculty member, we write a lot of joint proposals with universities. We actually wrote one, Candace was involved in that last spring. It was an EFRC proposal, which didn't get funded, but it's an example of how often we team with universities. And then we have university partnerships, as I mentioned, through our LDRD projects. We work with a lot of universities through that program. And we basically write one of these LDRD proposals, and then we can add a university partnership component of it that sometimes gets funded and sometimes doesn't. So we're very interested in, talking to professors and learning what you guys do so that we can see if there are opportunities for adding you onto a proposal and getting involved with you and your students. If you're a student, there's lots of summer internships. There's actually a ton of postings out right now. This is about the time when we do a lot of recruiting for summer. So if you're interested in an internship at Sandia, Now would be a great time to go on our website. There's a careers part and you can go to internships and see a bunch of listings there. You can apply to those summer internships. We also participate in some internships that are funded through other programs. There's one called the SULI program, which is the Science Undergraduate Laboratory Internships. And there's also in energy storage, an EERE energy storage program. I've had a couple of student interns that way, and these are really nice programs where you're paid through the program, but you go work at a national lab to actually do your research. So they're really nice. We like those. You should look those up and apply to them if you're interested. I believe the EERE one has open applications right now for students. And then if you're graduating soon with your PhD, we hire a lot of postdocs. We have somewhere between 150 and 200, I believe, right now. So we really do hire a lot of postdocs, and we're very interested in you applying to our postdoc positions. We have 2 fellowships for postdocs where you can write a proposal and a personal statement and give us a presentation. And then if you win those, there's about 3 of them a year. The 2 programs are Ruby and Truman Fellowships. If you win them, you actually get to work on your proposal. So as a postdoc, you get to be the PI of a project and run your own research project.
Just because I know there's lots of international folks here, are they eligible for the interns and postdoc positions as well?
That is a great question. So because of Sandia's mission as a national security lab, we do require clearances for a lot of our positions, but not all of them. There are interns, especially working at the Center for Integrated Nanotechnology, which I'm going to talk about in a minute. There are internships available for foreign nationals that don't require clearance, but most of us work in an area where you can't even go there without a clearance, and we have to do a lot of paperwork to have foreign nationals on site. And so it does create kind of a barrier at Sandia, but there are positions where that may not be required. So I'd recommend that you look at the postings and see whether a clearance is required for the specific posting, and that's how you'll know whether it would be a good path to try. I will say that there's only 3 national labs where national security is really the focus. So at Sandia, Los Alamos, and Lawrence Livermore National Lab. There's many national labs where most people do not have clearances. And you might have more luck if you're a foreign national getting a position there. So I'd recommend looking broadly at national labs and looking for opportunities.
And you'll talk more about that this afternoon.
Yeah, I can talk with students more about that this afternoon. Feel free to ask me lots of questions about that at the meet and greet later. Yeah, so great question, and a common question that we get. I've actually had foreign national postdocs and students, so it does happen. And then the other way that you can work with Sandia is we have a funded Center for Integrated Nanotechnology. This is a user facility, and it's outside of the normal Sandia base it's located. And this is not a problem to be a foreign national at all. We have lots of foreign nationals that work at the Center for Integrated Nanotechnology. And this is a center that's set up where you can work with the staff at Sandia that are experts in nanotechnology, and we have lots of characterization equipment you can use at SINT. And you basically write a user proposal. There's deadlines, I believe, in September and March, and you write a 2-page proposal, and then they get reviewed, and a certain number of them get selected. You can go to their website to look for what sorts of tools they have available and opportunities. And then if you're selected, you can travel to SINT and send a student to be trained on these tools that we have and to work with the scientists, and that's completely free. So that's a really good opportunity as a way to get access to tools that you may not have available at your university. So I encourage everyone to apply for SINT proposals, and I work very closely with SINT. I'm not a SINT scientist, but I've written a lot of user proposals with them, and I've worked there quite extensively. So many of the tools that I'll be showing in this talk are actually located at SINT and things that are available for user proposals. As a student, I always like to see how people got to where they ended up. So I figured I'd talk a little bit about my career path and how I ended up as a staff member at Sandia. So I was an undergraduate at the University of California, San Diego, and I graduated in mechanical engineering. I did a lot of undergrad research in both mechanical testing and biomedical engineering projects. And then I had 2 summer internships at Lockheed Martin, where I did satellite vibration testing. So that was, I think, a really good approach, is to try and get a bunch of experiences so that you learn whether you like being in industry, you like doing research. And I'd also try and get a position at a national lab if you can, so that you get a lot of variety on sort of what sorts of settings you like to work in. Then I went to UT Austin and worked on my master's in mechanical engineering. I worked in the thermal fluids systems focus area. And the research that I did there was computational fluid dynamics, as well as heat transfer experiments on gas turbine vanes and blades. And what we were trying to do was make gas turbine cooling more efficient, so that you would have airplanes that fly more efficiently. Then I took a class in batteries, and I just loved electrochemistry. So I switched my focus area for my PhD to the materials science area and worked with Armut Mantharam there. I had a National Science Foundation Research Fellowship to do my PhD work. So that's another thing I'd encourage everyone to apply for. This is a fellowship where you write a proposal as a graduate student and a personal statement, and then they select some people to get this National Science Foundation Award. And then your PhD research is paid for through the fellowship. So you have a lot of flexibility on what you can work on, because your professor isn't paying your funding through their contracts. So that's a really good opportunity that I'd encourage everyone to apply to as well. During my PhD, I worked on microwave solvothermal synthesis of battery materials, and then I did a lot of materials and electrochemical characterization on those materials. I was also president of the Electrochemical Society student chapter at UT Austin, and that gave me a lot of exposure to talking to people we would invite for seminar series like this one. So I'd encourage you to get involved in student chapters as well. It's a good way to grow your network and start, expanding your opportunities. I also had the opportunity to work with Oak Ridge National Lab a lot during my PhD. I got to travel there and do some experiments with them and work with the scientists there on collaborative projects that we had. And that was just an excellent experience for me and made me very interested in the national lab system. So I knew I wanted to try and get a postdoc at a national lab, and I applied to one at Sandia. I worked with Kevin Zabadil there on the Joint Center for Energy Storage Research, which is an energy innovation hub and was a huge conglomeration of universities and national labs working on energy storage problems. So that was really fun. That was run out of Argonne National Lab. And in that program, I worked on Langmuir-Blodgett deposition of graphene oxide to use as a model system for electrochemical testing of materials. And then I did a lot of in situ electrochemical atomic force microscopy and a lot of in situ electrochemical transmission electron microscopy. And so I had a great experience doing that and was eventually converted to staff at Sandia National Labs. I've done a lot of power source design and development there. I've been the PI of several internally funded LDRDs. That was that program I talked about. And those were all focused on batteries and other aspects of electrochemistry. And then I'm also currently the thrust lead for a Silicon Consortium project, which is a big 6 national lab consortium focused on silicon anodes calendar aging problems. And that's a consortium led out of NREL. So there's lots of opportunities for good collaboration. And in these LDRDs that I've had lots of collaborations with universities. So these are good ways to get involved. Now, finally get to my seminar and talk about some research. So this is a schematic of what a battery looks like, a cartoon. We typically have an anode and a cathode in a battery, 2 electrodes that are separated by an electrolyte and a porous polymer separator. I'm showing the anode here in blue and the cathode in red. And typically the anode is composed of graphitic carbon and the cathode is composed of a transition metal oxide. And the way that a battery works is, at least a lithium ion battery, and this is the type of battery that's in your phone or your electric vehicle, your laptop. We have lithium ions that reside in the system. They move from the anode to the cathode during discharge. And then electrons move across the external circuit to balance that charge. And those electrons are how we actually get electricity out of a battery. But there's always a mirrored process inside where we're moving the lithium ion back and forth. And you can think about these anode and cathode materials as being like hotels with rooms in them available for the lithium to reside in, and they just move back and forth between these sites. Those are usually things like interstitial sites in crystal lattices of materials, and they just happen to have a good space for lithium to be able to go into and out of easily. And so those are the types of materials we use today in lithium-ion batteries. Now, we all would like batteries to be smaller and weigh less for our devices. And so there's a constant push to get to higher energy density materials for batteries. And so one of the ways that we could do that is getting rid of these host structures that we're using. So that graphitic carbon is basically wasted space and mass, because all we really need is to convert the lithium ion to an electron and lithium metal. And so if we could do that without a host structure, that would improve our energy density at the anode quite a bit. So what a lot of people are trying to do in the research community is to replace graphite with lithium metal. And basically the way that that would work is you would electroplate the lithium metal and then electrodissolute the lithium metal with every charge-discharge cycle. So theoretically, that leads to about a 10 times increase in gravimetric charge storage capacity on the anode, and that can lead to big increases in energy density of the battery. So that's the motivation for the work I'll be talking about. We really care about increasing energy density of batteries. So why hasn't this worked, and why aren't lithium metal batteries in your cell phone today? Well, lithium metal electroplates in an uncontrolled morphology. We'd like it to plate like that on the left, where it's just a nice dense block of lithium, but it doesn't actually do that. Instead, it forms these high aspect ratio structures that look like dendrites. That's what we tend to call them, or mossy structures. And those mossy structures and dendritic structures can actually short circuit the battery by growing through the separator and cause fires and safety problems, as well as performance problems. We typically measure with batteries the Coulombic efficiency. That's basically the percentage of charge that we put in during electroplating that we can recover during electrostripping. So we plate some lithium, and then we try and strip that lithium away, and we don't get all of it back usually. And the reason that we don't get all of that back, and that Coulombic efficiency is below 100%, is because we form what's called the solid electrolyte interface, or the SEI. The SEI is a film that's formed from parasitic reactions between the lithium metal and the electrolyte. And the electrolyte is not chemically or electrochemically stable with lithium metal. And so that's why we have this problem, but we like to operate in the voltage range that we do because it gives us higher energy density and higher voltage. So we're sort of stuck with this problem where we're unstable, but we really want the energy density that affords. So that SEI formation leads to irreversible lithium and electrolyte consumption. So we lose some of the material in our battery that's active. And it also leads to high impedance in these cells, which can also be a problem for trying to run them at high power. The other way that we can lose lithium, and that this process doesn't work very well, is that we can form dead lithium, where the lithium that forms in these high aspect ratio structures can disconnect and become not connected to the current collector, so that we can't change it back to strip the lithium and make it ions and electrons anymore. So those are some of the problems that the community wrestles with lithium metal anodes. So there's a lot of strategies for improving lithium metal anodes. One of the most common ones that people try and work on is to replace the electrolyte. The electrolytes that are used in your lithium ion batteries do not cycle lithium metal very well. And so we try and replace the electrolytes with things that are more favorable for lithium metal plating. One of those electrolytes is 4 molar lithium bisfluorosulfonylimide in 1,2-dimethoxyethane. And this is a mouthful to say, so we just call it 4 molar lithium FSI and DME. This is some work from PNNL that came out about 7 years ago. It's a really beautiful paper where they use this electrolyte to show that you can deposit and strip lithium very efficiently. The Coulombic efficiency is high, and you get this very nice nodular morphology that does not look dendritic or very mossy. So this was really nice work, and it sort of started this whole branch of research into electrolytes for lithium metal that are based on high concentration electrolytes. And the idea is that you're trying to complex all of the salt with solvent, so you don't have a lot of free solvent lying around that can just react with the lithium. So this is really about coordinating all of the free solvent and stopping that reactivity. So there's a ton of electrolytes now where people have had the same sort of concept of the very high concentration to better control this process. But this is the one that I'll be using throughout my talk. So I wanted to introduce this really nice paper. I'm also going to talk about a few different types of electrochemical cells where we can study battery performance. The first one is an in situ scanning transmission electron microscopy cell. So this is a cell custom designed at Sandia that goes in a TEM, and we can do imaging with the TEM while we're running the electrochemistry with this cell. We also will be looking at coin cells, which is the type of battery that is in something like a watch. And we'll be looking at pouch cells, which is the type of battery that is often put into a cell phone because you can change the size and shape really easily with this type of cell. Now, I'll be talking about what we refer to as half cell testing. These can also be called anodeless cells. And these cells in their initial state are built such that there's lithium on copper as our counter electrode. We have an electrolyte and a separator, and then we have a copper working electrode. And what we're going to be doing is plating a certain amount of lithium onto the working electrode from the counter electrode electrochemically. And then we're going to strip away that lithium and move it back from the working to the counter electrode. We measure the coulombic efficiency of that process. Like I mentioned, it's the amount that we're able to get back that we were initially plating onto the working electrode. And this is always less than 100%, or should be always less than 100%, because we have dead lithium formation and we have that SDI formation that occurs. So we can't get more electrons out than we put in, and some of them get wasted to these parasitic processes. So we have to have a coulombic efficiency less than 100%. So I'll just mention that these are all idealized cells. These are not cells with a cathode and an anode, like a battery that would actually deliver power. And we often do that in the research community and call these half cells because we want to isolate what's going on with the lithium. And the best way to do that is to just have these very simple cells that are focusing on one electrode material rather than having a cathode and an anode and having to try to deconvolute what's happening with both of them. So this is an outline of the seminar, and I'm going to talk through these papers that I list here. The first one is a paper that sort of motivated all of the others, so I'm going to start with that. And then we're going to talk through the effects of pressure on lithium metal anode plating and stripping, and that was all motivated from this initial paper. So the motivation for this paper was actually not studying pressure, but it was to understand the lithium growth progression in this 4-molar lithium FSI and DME electrolyte. We saw that beautiful morphology that formed, and we wanted to understand why. How does it nucleate? How does it grow? So we wanted to do that inside of a TEM so that we could run electrochemistry and just sample images at various times as the lithium grew. And Sandia has sort of a unique approach to electrochemical TEM. This is something that's located at that Center for Integrated Nanotechnology that we have. We created these bottom and top chips that are shown here. And what we do is we have electrodes on this chip, passivate the entire bottom surface of this chip, and then we go in and use e-beam lithography to pattern smaller electrodes everywhere that we want to be able to view them, and everything else is passivated. The reason that we do this is we want to be able to make sure that our electrochemical signals that we're measuring are completely correlated with where we're imaging. So if we didn't passivate these and draw these smaller electrodes in, then we can't say that what we see is the entire story of the electrochemical signal. But we're only doing electrochemistry in this cell on these tiny little electrodes that we have patterned on. So after we do that, we put the two chips together. They each have a silicon nitride window that align. And that silicon nitride window is very thin and allows the TEM beam to go through the cell so that we can image while we're doing the electrochemistry. We epoxy seal these two chips together. Then we take them into a glove box, fill the cell with electrolyte, and we epoxy and tape over those holes, which were the fill ports. Then we wire bond this whole chip to a chip carrier, put it into a TEM holder, take it into the TEM, hook it up to a potentiostat, do electrochemistry, and then we can image as we're actually doing that electrochemistry. So these are the types of images that we're able to get from these TEM experiments. These are bright field TEM images. So we have white lithium that's shown here, and the darker colors are for denser metals. So you can see that we're able to grow lithium on these electrodes. And then when we try and strip that lithium away, we see a lot of it ends up still on the electrode, and we're not able to get rid of it, which means that there's dead lithium forming, and our coulombic efficiency is very low. So we are able to get realistic electrochemical curves, but this is kind of baffling because we were expecting to get the nice morphology and the high coulombic efficiency in the Nature Communications paper that I introduced earlier. So we thought a lot about what the various things are that are different in our TEM experiment versus a coin cell, because clearly we weren't replicating something correctly. And the most important thing that we thought to look at first was the effects of applied pressure. In a coin cell, we have pressure on the interfaces, and so all of that electrochemistry is taking place under pressure. In the TEM cell, we really can't do that because the place where we're imaging is thin and delicate, and we can't put pressure on it and still be able to image at the same time. So we did an experiment outside of the TEM where we replicated a cell with pressure, coin cell type of cell, and we get much higher coulombic efficiency, and we're able to replicate the beautiful morphology that was shown in this paper. Then we took a beaker, a cell without any pressure, and we did the same experiment. And we get very low coulombic efficiency, and the morphology is much less well controlled. And we see clear evidence of dendritic growth of these lithium deposits. So what this tells us is that even in these really promising high concentration electrolytes, we are still having problems with dendritic growth, and pressure is a critical parameter for controlling this lithium growth. So in that paper, we saw that pressure mattered. We know that that's important, but we didn't quantify the pressure in any way. So what we set up to do is a systematic study where we look at the effects of pressure over various ranges and try and figure out what the impact is as we vary the pressure intentionally. That led to the paper that is outlined here. So we built pouch cells for this study because pouch cells are easy to apply pressure to, whereas a coin cell, it's much more difficult to control the pressure. We have a counter electrode, we cover it with a separator, we add a working electrode, and then we seal the cell. And we used a variety of devices to apply pressure. We used these weights for very low pressure because they keep a constant force on our cell. And then we built these piston-like devices with load cells and a feedback control program that kept the pressure constant for intermediate pressures. And then we used commercial load frames for the highest pressures. This is what the electrochemical performance looks like. So we have from red to gray, increasing pressure as you go down the screen. In the left, we're looking at the charge storage capacity of the lithium on the left plot versus cycle number, the number of times we've charged and discharged the battery. And then we're also looking at the potential as it varies with time in these cycling experiments. So what we see is that the cycling stability generally increases with pressure, but it stops getting better when we get to 10 megapascals. We see that 0.1 and 1 megapascal are pretty similar in terms of their stability, but that 10 megapascal really looks a lot worse. We see a huge increase in what we call the overpotential, and we see a decrease in cycling stability. And I'll talk a bit about overpotential, so I want to explain what that is. So in equilibrium conditions at very slow kinetics, we would expect the lithium to plate and strip at zero volts. But if we have kinetic limitations in our system, then we have to apply more voltage to get these reactions to go. And so the size of that increase in voltage is what we call the overpotential. And there's various sources that cause the losses that lead to that overpotential needing to. These are all galvanostatic experiments, which means that they're constant current and we're measuring the voltage. So if we're putting in a constant current, the voltage has to adjust itself in order to be able to run the electrochemistry. So the transport, we hypothesize that the reason the high pressure doesn't work very well is because we can shut down pores in our porous polymer separator, such that transport is limited and we are essentially not able to move ions quickly enough in this cell anymore. So I'll talk more about that in a few slides. But first, what I want to show you is the morphology evolution with pressure. So in these experiments, we're using cryogenic focused ion beam milling, gallium beam in this case, and scanning electron microscopy imaging. This is after one deposition of lithium onto copper on the working electrode. And these are the cross-sectional images that we see. We use cryogenic imaging because lithium is a very sensitive metal to beam and temperature. And so we like to freeze it and then know that we're not doing very much damage to the lithium. So you can see that the morphology expands a lot when we go to lower pressures, and we're able to get much denser morphology at higher pressure. That correlates pretty well with first cycle Coulombic efficiency as well. And we see that at 10 megapascals, the Coulombic efficiency in every replicate we've tested is over 100%. That's a problem. That means we likely are forming short circuits even on our very first deposition and stripping cycle. So clearly the pressure has a huge impact on morphology at the current that we're looking at here. We next looked at cryogenic fib and SEM at the 51st cycle, and we wanted to see if the pressure only mattered in the beginning or if it continued to matter throughout cycling. And you can see that the morphology continues to be denser and better controlled at higher pressure, even as we go to these longer cycle lengths. So we were motivated to kind of understand why pressure actually matters. I was talking to one of my colleagues, Steve Harris at Lawrence Berkeley National Lab, and he posed the question, why does pressure really help when real surfaces are rough? You've got this big pressure distribution. The separator's really soft. Aren't you just going to be squishing the separator? And then we're really operating at pressures that are generally considered to be lower than the yield stress of lithium. So we aren't plastically deforming the lithium. It has to do with something else. So we started collaborating with this group at Northwestern that did a lot of the work for this paper, and they were an expert in mechanics modeling, and we thought it would be very interesting to look at this problem that way. So this is a schematic of the type of system that we're looking at. We're simulating rough surfaces on the anode and the cathode. We have a separator in the system, and they just used a contact mechanics type of model to understand if you apply a certain amount of pressure and the lithium is growing, how is that pressure going to be distributed when you have these rough surfaces, and how much of a variance is there going to be in the pressure? So what we're looking at here is the gap between the lithium and the separator. And white means that there's no gap, we're in contact. And if it's colored and more so red, we're looking at a larger gap where there's space between the separator and the lithium. So they included a lot of things in this model, including creep and mechanics. And we looked at the effects of lithium growing and causing an increase in pressure because of the volume change. And then what they did after they got these images was throw the pressure distribution into what we call the Butler-Volmer equation, which is an equation to understand the kinetics of an electrochemical reaction at an interface. And in that equation, there is a term that is related to pressure and mechanics because you have to do work to move something mechanically. And if you plug the changes in pressure into that equation, you get that there will be about a 16 millivolt variation in the overpotential that you will need to drive this reaction in a high pressure region versus a low pressure region. And so that means there's an incentive for lithium to plate at the low pressure regions because we don't have to pay the penalty of this overpotential. The way we can think about that sort of more physically is that when you're needing to displace an interface, so let's say we have lithium under pressure in a certain area, if you want to plate more lithium in that area, you have to move that interface. That takes work, pressure volume work. And so it's easier for the lithium to deposit in the low pressure region because you don't have to do additional work in order to move that interface. So that gave us some insight into how the lithium or how the pressure can control lithium growth, even in a system that's real with rough interfaces. And that was a really, really nice model. It didn't include some of the things that we were interested in, including transport and a little bit more sophisticated electrochemistry. And so we started collaborating with a group at Purdue University, Julia Meyer and Partha Mukherjee, as well as Scott Roberts and Sandia, all modeling experts. I'm the only one that was useless to do any modeling on this project, but I was very interested, so I motivated the project. And we looked at a slab of lithium with a rough surface and a separator We move those two surfaces into contact such that there's a pressure applied and do a linear elastic model, remesh that electrolyte region, solve for the pressure. And then we also include things like strain in the separator and the possibility of pore closure if that strain gets too high, and solve for transport in the electrolyte region in the gap space and in the separator. And so by doing that, we can actually understand how that pore closure changes the transport of lithium ions and the ability to actually form lithium at the surface. So this plot on the upper right is showing the reaction rate at the surface along that sort of diagonal between the peak and the valley. And what we see is that the reaction rate drops to 0 when we have high pressure. And that's because pores close in the separator. We're no longer able to transport lithium ions to the surface in that location. So we can't have current and reaction of lithium there. But as we go out from that high pressure region, we will see a spike in the current because you have a constant current that you're applying. If you shut it down at some area, it has to be higher in other areas. And so this leads to plating in the areas of low pressure because you can't plate in the areas of high pressure. But it also leads to a lot of inhomogeneity in the current. And so this explains that we should see the protrusions sort of even themselves out because they're more likely to go to the low pressure regions if we shut down those pores. But it also means that we're going to have these current spikes. And we know very well from the literature that lithium will plate and in these dendritic morphologies at very high currents. And so if we have these current spikes, we're likely to get dendrites. And so we think that's why we were seeing at the highest pressures this unstable lithium plating because we're shutting down transport and because we're forming dendrites. So everything I showed you in that last pressure study, that experimental pressure study, was at low current density. Now we wanted to repeat that study at high current density where we actually expect dendrites to form. And we wanted to see whether pressure would stop the dendrites by just pushing on them, or whether we would see these transport problems arise and we'd make the dendrites worse. So first I want to show you morphology of the lithium metal that we plated at these various pressures. I'm not showing you 10 megapascals because we could not plate lithium at this current density at that pressure. And we think, again, that's because we shut down transport. It's already limited at the high current density. We add the pressure component and we can no longer do electrochemistry. But what's striking about these images is if you recall what I showed you at low current density, we saw a huge variation in the thickness of the deposits and the morphology with pressure. And we don't see that at all here. We really see very little difference with pressure in how the deposits look and the thickness of those deposits. So why is that? We've thought about this a lot. And we think that what's happening is that at low current density, lithium can nucleate and grow at very favorable sites on the surface. We don't have transport limitations or kinetic limitations. So if we're driving at a very low current density, we can have these sites on the surface, defect sites, for example, where lithium would prefer to grow, and it'll nucleate there and then just continue growing there because we can move lithium ions as easily as we want. We can move them all over and we don't have to plate in non-favorable regions because we have enough time, since this is a slow current density, to move the lithium ions to those favorable sites. Now that means that the overpotential related to mechanics and doing work to displace the interface can be a major component because we don't have a lot of overpotentials in the system. We're not kinetically limited or mass transport limited. And so that mechanical overpotential can play a huge role in where the lithium will deposit. And so that mechanical overpotential is going to dictate that we're going to start plating in these low pressure regions and even out the morphology because we just don't have a lot of other competing overpotentials. At high current, we have lots of overpotential related to kinetics and related to transport. And so now we have a totally different story. And since those other overpotentials are so large, the mechanical overpotential doesn't play a role because it can't compete with those. And there's other bigger barriers in the system. So we don't see a change in the morphology because that's not what's controlling it at that point. Okay, so let's look at the electrochemical results. We, again, are not showing 10 megapascal because we could not run the electrochemistry. And I'll just note that the only cell that was able to cycle continuously for 50 cycles without starting to lose capacity at the end of cycling was at 1 megapascal. So it appears we're getting better performance at higher pressure, but there's a lot of caveats to that. We also see that the coulombic efficiency generally improves with higher pressure, but I'll note that many of those data points in that upper right-hand plot are above 100%, and that makes us really suspicious of short circuits. So I will say that we can have coulombic efficiencies above 100% in a cycle or two. That's okay, because you can get dead lithium that forms on one cycle, reconnects in another cycle, and then it'll be low on one cycle, high on the next. As long as it averages out to less than 100%, we're okay. But what we did to kind of understand that better is to look at the cumulative average of the coulombic efficiency, and that's shown in the bottom right. And you can see that even if we average the coulombic efficiency, we're over 100% in all the cases except at 1 megapascal or at 0 megapascal. So only our cell that's under no pressure is performing without what we would suspect are short circuits. So this begs the question of whether pressure is exacerbating dendrites rather than squashing those dendrites. That's our first clue that that's what's going on. We really wanted to look at longer term cycling where we were seeing more of those discrepancies. And we showed this for the low current data where we looked at 50 cycles, but we couldn't use cryo-gallium fib like we did in that study because when we tried to take apart these cells to get these ex situ samples for the cryofib process, we really felt like we were having to rip apart these interfaces. And that also made us think that maybe we had some short circuits and lithium growing in the separator. So because we felt like we were damaging those interfaces, we were worried that we were destroying any evidence we might have of dendrites and that this wasn't an appropriate technique to be using. This motivated us to try and figure out a way that we could mill through entire electrode stacks without having to pull them apart. That really isn't possible with gallium fib because it's a very slow milling process, and we just really can't get through the number of microns we need to be able to do that technique in this way. So my colleague, Katie Young-Johan, who's a microscopy expert that I work with a lot and has taken a lot of the images in this presentation, had this idea to try a different type of technique for this exact problem. And that led to the paper here, which I'll talk about a little bit. And then I'll come back to that study where we eventually were able to look at 50 cycles using this technique. But I want to explain first how we do it. So my colleague, Katie Young-Johan, had learned of this new instrument that Thermo Fisher was making called Helios 5. And normally you have a gallium ion beam that comes in and mills through your sample. And this instrument was different in that it had a femtosecond laser, and that could athermally mill through material about 15,000 times faster than gallium fib. So this is kind of a game changer for what we're able to do. So Katie had this idea that maybe Thermo Fisher would be willing to put a cryo stage on this instrument, and maybe we could take a coin cell up there and see if we could just mill through the entire thing. It's necessary to freeze the cell. If you don't, then the electrolyte will just evaporate and muck up your system and cause all sorts of problems, including short circuits, right, while you're milling, because you need your electrolyte to be frozen so you're not short circuiting your cell with the milling process. So they were susceptible to that. At this time, it was a research tool and they weren't selling it yet. And so they let us come there and do a lot of experiments, and they did a lot for us too eventually. And we were able to get a lot of images with this method. So we put the coin cell on the cryo stage, we mill through it, and then we polish those images. And this is the type of thing we're able to get out of the experiments. So this was a coin cell that was cycled 100 times at low current. You can see that we've artificially colored it to make it easier to understand. The top is a copper current collector working electrode shown in peach, and the bottom is counter electrode. And we have pristine lithium that's shown in pink that's on the bottom of the electrode. We have excess lithium on the counter electrodes. That's why there's so much lithium left over here. And the way that we're able to identify what's lithium and what's not is because the laser interacts with the lithium and produces a pattern that has a periodic structure that's unique to each material. So shown up there in the upper right, you can see that lithium produces this periodic pattern that is easy to use as a fingerprint. And there's an image of an impurity in there that has a different laser-induced pattern, for example. So we would zoom in on these images. Katie would spend a lot of time on this. And she would find all of the areas where we actually had lithium metal present in a bulk form that showed this fingerprint pattern. And you can see that there's also this blue region that is our separator that we can also pick out pretty clearly. But then there's all this other gray junk that we can't really assign. And what we would really expect to see is a bunch of pink lithium on the bottom and pink lithium on the top, right? But that's not really what we see. On the working electrode, it's very hard to pick out regions of bulk lithium. So we think that this gray stuff is a mixture of electrolyte, of SEI that forms, and of dead lithium, disconnected lithium, and very small domains of lithium. If the lithium is small enough, we won't see that laser-induced pattern because it's just too small and smaller than the wavelength of it. So we've sort of colored this to explain what's going on. But overall, this looks pretty good, right? This cell isn't shorted. It looks really nice. There's no evidence of any real problems here. The electrochemistry is beautiful and repeatable over all of the cycles. So this is about what we would expect to see. Now, if we go to a high current, the performance and the images are completely different. At this high current, the cell actually failed. I'll mention this is a slightly different current and electrolyte concentration than what I use in the rest of the talk. So there's some differences here that I can go into if anyone's interested. But if we look at the upper left-hand image, we see that we've got our copper working electrode, our separator under that, our pristine lithium, this is an uncycled cell, and then our copper counter electric current collector. And so in the first deposition, we can see we plate lithium onto the working electrode, we strip it from the counter electrode, we see lots of evidence of bulk lithium along with some SEI regions. And then we strip that away and there's a bunch of material left, right? We don't get it all back. Some of it turns to SEI and we can still see some bulk lithium there that must be disconnected or dead lithium. After 1 and 11 depositions, we actually start to see some evidence of junk forming in the separator that doesn't look like separator anymore, that we think is infiltrating the separator with SEI, potentially lithium deposits. And then by 101 depositions, we know the cell has failed. We're no longer able to deliver capacity, but we also see that it's failed very clearly in our imaging. The separator has been completely shredded by the lithium, and now it's just all sort of intermixed and intertwined. And so this is not good. This is not what we want. Separators are there for a very particular reason, to prevent the two electrodes from shorting together. We really need that separator to work, and we need it to stay intact. So the fact that the lithium destroyed the separator through its growth process is not a good thing, and it explains why the cell failed. It's a little bit surprising that lithium was able to do this. It's a very soft metal, and so you wouldn't necessarily think it would be capable of destroying a polymer separator. But we do also have SEI capping all of that lithium, and so it's possible that that ceramic layer of the SEI makes the lithium hard enough to destroy this separator. Okay, so that was a really interesting study that we did, but the point of it was really to get back to this study where we looked at the effects of pressure on lithium plating at high current, and we wanted to be able to cross-section those cells without pulling the interfaces apart. So we talked about this already, but I told you that I would come back to it, so that's what we're doing now. And we basically looked at this laser process to mill through all of the cells. On the top right, you can see that we have a cell, and I'm sorry, the coloring is different now. The separator is now shown in purple. The lithium is green, and the current collectors are still that peach color. So we have a beautiful cell. When we haven't cycled it, everything looks great. But after 100 or 50 cycles in this case, you can see that the separator starts to delaminate and starts to break apart. We don't see the same shredding. Again, this is a slightly different current density and concentration of the electrolyte, but we do see a lot of separator damage where we start to see infiltration of SEI and potentially lithium into the separator region. But we also see this green stuff, the lithium metal, starting to form between the separator layers. So this is clear evidence that we're growing lithium into the separator. And what you can see is that as we increase pressure, we get more and more lithium growing into the separator. So this really goes with the theory that the pressure is exacerbating short circuits. It's causing us to grow lithium into the separator. And increasing pressure when we have current is probably not a good idea because it exacerbates the transport problems and causes shorts. So that's all I've got. In conclusion, pressure has a significant impact on lithium metal anode performance morphology. I showed you that at low current density, when we apply pressure, we can improve morphology and coulombic efficiency. And the plating really will occur at the most favorable sites because there is not much in terms of transport kinetic restrictions at low current. And that means that plating will be dictated by the mechanical overpotential instead of these other overpotentials. And we really have to do work to displace the interface to plate at high pressure regions. So we instead plate at low pressure regions, and the mechanical overpotential controls that growth process. Too much pressure, it has to be a lot more pressure, something like 10 megapascals, will actually lead to dendritic growth because of the inhomogeneities in local currents and local transport restrictions. At high current density, the story is different, and applied pressure has less impact on morphology, but it can still impact performance. Transport is very limited and kinetics are limited in general, so we get more compact and uniform nucleation and growth, and that's favored because we just have to plate everywhere if we're trying to keep up with that high current. The applied pressure exacerbates transport limitations, and so it actually exacerbates dendrites rather than squashing them. So with that said, I'd really like to thank you for inviting me. It's been a really fun trip. I want to thank you for all your attention and really my sponsors and collaborators. I've had a ton of people that helped with this work. So thanks, and I'd be happy to take questions.
All right, if we have questions in the room, we can take them. Anyone online, if you have a question, please put it in the chat and I can ask it for you. Yeah.
Very nice talk. So the work that you did with Katie on the laser ablation is very, I mean, there was huge areas that you were able to expose, but of course the laser is subliming the material. So I wonder how hot it gets, and when you were showing those microstructures where you had mixtures of the SEI and, you know, disconnected lithium, I wonder, you know, have you thought about, you know, the sort of radiation damage aspect, especially since you're using SEM to look at the surface, which is going to be the most damaged part?
Yeah, for sure. So we do think, so these are cryo temperatures, so we're dealing with heat very well from that perspective. And it's also a femtosecond laser process, so it is supposed to be an athermal process. So it's not, yeah, it's pulsed, and we can control that. You know, I don't actually know. It's in the settings, and I could look it up, but I don't have that information. But it is, there are other laser milling systems that don't work for this because they aren't the femtosecond process. Like, we're using this specifically for the athermal properties. Yes, exactly. And so it is really important to use that particular instrument. We did look around a little bit and try and find others, but this was unique for that particular purpose. And so I think that we're doing okay with heat, but and we would really see the electrolyte start to evaporate if we weren't doing a good job with heat. And we do see that sometimes, not through the milling process, but we've seen evidence of things going poorly when we start to do EDS because we're operating at higher voltage then. And so we've seen that we have to be a little bit careful under some conditions. We've also tried to do this with pouch cells. So everything I showed you was a coin cell, and I kind of cheated a little bit and didn't explain this top portion, but we have to use coin cells with this particular process. And we were using pouch cells with these pressure studies, right? So what we did is we opened up the pouch cells and using ceramic scissors would cut a coin cell sized hole in our pouch cell. And then we would put those in a coin cell as a way to protect them to get to the SEM. And then we'd freeze it all in the SEM. And the reason we have to use coin cells is because we can't keep the pouch cell cold enough. And if we try and do this with pouch cells, which we have, we actually will see heat that will have electrolyte coming off, and it starts to boil, you see bubbles. And so we're pretty confident that we keep it cold enough because we know that the electrolyte boils off when we don't. And we'd like to have a bigger cryo stage that's more powerful, but we so far haven't gotten it to work with pouch cells for that reason. But it's a very good question.
Thank you for your presentation. So I actually have a question here. So as you mentioned before, it's a little bit hard to control the pressure within the coin cell, but for here, is there a specific way you control the pressure on the medium?
Yeah, so we did all of this in pouch cells so that we could control the pressure better, and then we took them out and put them in coin cells. And we used about 100 kilopascals of pressure in the coin cell, but we don't think that that changed much at that point. Like it was sort of already, damage was done by the original experiments. We have done a lot of work trying to control pressure in coin cells too, and we've done a lot of work trying to change the springs out or stack springs and get to higher deflections to control pressure. But the problem with coin cells is that the seals aren't strong enough to withstand high pressure. So if you can get springs that will go to high pressure and you just compress them more, but you'll see that the cell starts to expand and the seals don't seal anymore. So coin cell crimp seals just aren't strong enough to withstand more than about 300 kilopascals of pressure.
Thanks very much for an excellent talk. First of all, I think for the low pressures that you have, I believe there is no phase transition seen in the lithium. It's still on the HR9 phase. Okay. If that is the case, then do you have any experiments where you've sort of Fourier transformed the image to see what the radial distribution function looks like and see what those lithium distances look like?
We haven't. That would be a great experiment. We have not done it. Like you could do a TEM lift out and look at it, and that would be a great experiment. We have done I didn't talk about it today or connect it to this talk, but we have looked at XRD of these samples after plating at high pressure versus low pressure. And that's actually pretty interesting. We don't see a change in phase. We get the same lithium structure, but we see residual strength. And so we're able to do strain measurements by looking at angled XRD plots, right? And when we calculate what the strain is, it increases only when we're at high pressure. And so by having to deposit lithium under pressure, you induce strain in the crystal lattice of the lithium. But if you deposit at no pressure, you do not do that.
But that is still ex situ where you have cycled it back to
Yeah.
low pressure.
Yeah.
And all this is happening at high pressure. So it makes sense for you to do those measurements at high pressure.
Yeah. Agreed.
Because a lot of it that you presented, everything tells about the morphology, but nothing about the crystal structure
Yeah.
or the actual structure.
Yeah.
So maybe it's a good thought to actually see what the structural variation.
Yeah. All of that's been ex situ for sure. So you're right. And it could transition back when you take it out of the pressure state. The one reason I think that it doesn't is because we see that residual strain, right? So we've essentially like cold worked the material by putting it under pressure, and then it's trapped in that strain state. But you're right that it could change by the time we actually look at it and open up the battery. It's a really good point.
Thanks.
Katie, we have 2 questions on
Sure.
the chat, actually 3 now. So HP wants to know if there's a PhD opportunity for international students in your lab.
Right now, no, but I did have a foreign national postdoc one time, and it was great. I don't have an opportunity like that right now. I am looking for a postdoc, but unfortunately this postdoc has to be cleared because of the places that they need to be able to access.
Then Krishna has a question. Can you speculate on the role of non-hydrostatic stresses on dendritic growth? For example, tensile stress at the interface. And has there been any systematic studies on the role of interfacial coatings that could mitigate SEI deterioration?
Yeah. Sorry, I was stuck on the hydrostatic part. Can you reread the second part?
The second part was the role of interfacial coatings on SEI deterioration.
Okay, yes. Okay, so the first part of the question, everything that we've looked at is uniaxial stress. So this is not hydrostatic stress. It's unclear what exactly would happen in the battery, but it is more likely to probably be uniaxial stress, I would guess, unless there's gas that's forming to sort of compress everything more evenly. So we haven't done hydrostatic stress comparison. I have seen some modeling on that, I believe, but everything we've done is uniaxial and not hydrostatic. And then in terms of the coatings for the SEI, I actually talked about this I gave a guest lecture in the battery class yesterday and talked about that a little bit. So there's a lot of work on artificial SEI coatings. We've also done some pressure work on artificial SEI coatings because we were thinking that maybe the artificial SCIs would homogenate the nucleation and growth, and then maybe not be so dependent on pressure. And we have seen actually in that same ACS nano paper that kind of wasn't true. We still needed pressure to get good performance. And we've done that also with zinc oxide coatings, which is unpublished, but that basically is inconclusive so far. So I'm not 100% sure what the effect is on at least the pressure impact when you have a coating versus not. But we're working on that now.
We have a question from Hong Lu. He says, great talk. What is the pressure gradient in the cell? And have you considered using other electrolytes, and would there be any effect?
Yeah, so the pressure distribution in the cell is interesting. That contact mechanics model showed, we tried to get a realistic roughness for both the lithium and the cathode, and then, applied the contact mechanics so that would propagate through the separator correctly and all of that. And when we did that, I think in that image that I showed with the gap spacing, the variation when we applied 10 megapascals, I believe was about 0 to 30 megapascals. And so there was quite a distribution, and that leads to a lot of inhomogeneity. So if you're applying a certain amount of pressure, you may actually be applying a lot more in certain areas. And there's been a lot of work in the literature on this, even for lithium ion batteries, where inhomogeneous pressure distribution can cause a lot of issues. And so I think that's a really good point is, as you grow these systems and scale them up, the pressure is likely to get even more and more inhomogeneous, and that can lead to some problems.
Okay, any more questions from the room? Yeah.
You mentioned with Dr. Croker about the damage that happens to the LiFSI during the dipping. Have you ever done any sort of characterization that has to test the effect of local heating on the electrolyte?
We have not. So these are all done at cryo temperature. So the electrolyte is completely frozen, essentially during the characterization experiments, all of the imaging experiments. There has been some, well, actually, we have also done some work looking at performance at varied temperatures with the 4-molar lithium FSI and DME electrolyte and some of the related, they call them locally high concentrated electrolytes. So I do think that temperature is a super critical parameter because it changes everything about kinetics. It changes the conductivity of your electrolyte. It changes the surface reactivity, sort of the kinetics of electrochemical reactions, right? And so all of that is going to change which over potential is going to dominate, right? You're always balancing, is it going to be the activation over potential, the concentration over potential, the IR drop, the mechanical over potential, or some other factor in the system. And when temperature affects all of those things, these conclusions may be completely different at minus 10 degrees or 60 degrees, right? So I think that that's really important. And how do you even design a battery for room temperature if pressure helps at low current, but it isn't good at high current, right? So then if you throw temperature in, it's just, that's why batteries are so complicated. There's so many parameters that can make a difference.
We have another question on the chat. So Chingbo is asking, how do you measure the porosity of the samples? I guess that's referring to the lithium when it becomes mossy.
Yeah, so we don't measure the porosity. All we measure is the thickness. You could back out a porosity knowing the capacity, although you can't account for SEI very easily in that. So we haven't actually tried to measure the porosity particularly, but we sort of could assume a porosity from the thickness.
And he's asking about this slide. He says that the thicknesses of the cells look different.
Yes, they are. And I took this out of the talk, but we've also specifically looked at how the thickness changes and what impacts that has on energy density. I didn't talk about that today, but I think that that's really interesting. And you'll also notice that these 3 images, they don't have any lithium left at the counter electrode. That's actually consistent with the electrochemistry because we ran out of lithium and we were starting to reduce the capacity. In that 1 megapascal cell, that was the only one that was still delivering capacity at the end of the 50 cycles. And it's the only one where we have lithium inventory left in the cell. So that all matches. If you remember, the electrochemical behavior looked better in the 1 megapascal cell. But personally, I think that's because it's shorted and we're not using lithium to apply the current. We're just directly moving electrons through the cell through the shorts. And so you might want to say that the 1 megapascal looks best from this, but we also know it's shorted. So I don't know that that is a reasonable conclusion. And so, the thickness being lower in that cell may only be because it's more shorted. So you aren't doing mostly electrochemistry, you're doing mostly direct electron transfer through the shorts. So it's tempting to say that's good, but I don't think it is.
We have another question on the chat. Bruno wants to know if pressure deforms the separator to the point that it changes its tortuosity or induces plastic deformation. What's the
Yes.
yield stress of the membrane and can it withstand creep?
Yeah, that's a great question. And we didn't look at that in particularly, but there's some really nice work by Craig Arnold. And he has looked at lithium ion batteries where he looks at the separator and tries to understand where it starts getting damaged. And I think in his results, he shows that at about 1 megapascal, you start seeing viscoelastic creep of the separator and you start to shut down the pores. And he has beautiful images just showing how the pores go away and sort of become this mess. And so we think even at 1 megapascal, we're probably getting a little bit of that. And that's more than you should use for cell guard separators. But we haven't looked into it. I just trust Craig Arnold.